machine is concerned, the output rating is the one which is actually mentioned on the nameplate details. If the nameplate details is going to say 1 kilowatt, that means this is output is 1 kilowatt. As far as the DC machine is concerned, we are not going to have any difference between kVA and kilowatt. There is no question of any power factor. So whether we look at the DC motor or whether we are looking at the DC generator, always the power will be given in terms of kilowatt and the power that is given is output. So if it is generator, we are talking about electrical output. And if we are talking about motor, we are talking about mechanical output. Clearly. So if I am talking about a 1 kilowatt machine in general, whether it is a motor or generator, 1 kilowatt indicates always the output. Nothing else. It is going to be output. And if it is a generator, I will have to specify clearly what is the terminal voltage and what is the maximum load current it can supply. Because I am going to assume that even if the armature current is slightly higher than the load current because of the fact that there is some amount of field current in a shunt machine, for example, but the field current is going to be really small, because of which we can kind of neglect it when we talk about the rating. That is the way we look at it. So I'm going to say that this is the load current my machine can supply. But when I am talking about how much I can overload a machine, we generally talk about it in terms of commutator capacity. The commutator is extremely sensitive to any increase in the current. So normally if it would be able to commutate a current of 10 amperes, maybe it will be able to commutate until 20 amperes, nothing more than that, twice. Generally many of the DC machines have the overload capability of 2 times the normal rated current. That is the way it is. Whereas if I am looking at a motor, right, I am basically looking at, first of all, what is the voltage that I am applying, because I am worried about the electrical quantity. So I may specify, even here we would specify prime mover speed. What is going to be the prime mover speed, right? And corresponding to that prime mover speed and a rated field current, I'll be able to generate the rated open circuit voltage, which will be slightly higher than the terminal voltage. The terminal voltage is 220. Maybe the open circuit voltage can be as high as 230. Slightly higher. It can be, right? So we are going to specify here rated IF, at which the rated voltage, the generated voltage will be at rated value, which can be slightly higher than whatever is my terminal voltage. That's why I'm getting regulation. Ideal generator, I should not have gotten this discrepancy, but because of RA, which is a finite value, I'm going to have internal drop, which is going to cause some regulation in this particular generator. This is true for any machine, whether we talk about synchronous machine eventually, whether we talk about transformer, whether we talk about DC generator, where we are talking about electrical output. Whereas, if we are going to talk about motor, normally we are going to say what is the rated speed. Rated speed is achieved when I apply rated voltage to the machine. The machine is drawing approximately rated current and I have given rated excitation and I am drawing rated torque or rated power from the machine. So everything is at rated condition. At that point, whatever is the speed that is being achieved is rated speed. So having seen the speed torque characteristics of the machine, if we say this is the speed torque characteristics of the machine, this is omega, this is TE, maybe this is what is TE rated or TL rated. whatever, because they are going to match with each other. Then you can very well note that this is the speed at which the machine is going to run at this particular rated torque condition. So this is omega rated, whereas this is omega no load. This is omega no load. Omega no load definitely will be slightly higher than omega rated normally in any machine, right? This is true in induction machine when it is working as a motor. This is very true in the case of DC machine when it is again working as a shunt motor or separately excited motor. This is not true only in synchronous motor, because synchronous motor will run at a particular speed or does not run at all. So you are going to have basically the speed to be at synchronous speed no matter what. So you will not have a drooping characteristic at all. You will in fact have in a synchronous machine a steady characteristics like this. I mean, it cannot come down. It should be a straight line, horizontal straight line. So this is my synchronous speed no matter what, whatever is my torque. This is how the synchronous motor will be. So this is your synchronous motor characteristics, whereas this is separately excited or shunt motor characteristics, right? So in the motor, what we specify as electrical quantities will be what is the voltage I am applying, that is VA or V in general, and what is the maximum line current the machine can draw, which will consist of both armature current and field current if it is a shunt machine, right? And we are going to say that this is the maximum kilowatt that it can supply. So if I say Vt multiplied by IL is the total power drawn by the motor, this will be greater than the kilowatt output, clearly, because the efficiency cannot be 100%. Clearly. And kilowatt output, what is measured, is mechanical in nature. So it is torque multiplied by speed. And loading a generator, you will do it by connecting a resistance if it is a DC generator. Loading a motor, you will do it by maybe holding the shaft, putting a brake, right? If it is a grinder, you will put more and more material to be ground. So it is essentially causing impediment. It's not allowing it to freely rotate. So always when the machine rating is given, it is given in the form of output, unless mentioned specifically that we are talking about input, unless mentioned specifically. The nameplate details always give the output. Okay? In the case of induction motor and so on, sometimes they may say at what power factor it will work under full load condition. Because induction motor, we also said, when it is actually starting off on no load, the major current drawn is only magnetizing current. So normally induction motor power factor is going to be very bad during no load condition, because what the rotor carries, the rotor current is very minimal, whereas I am going to have magnetizing current is the major portion of the no load current. So the power factor can be as bad as 0.2 or 0.3. The power factor can be as bad as this. Transformer power factor could also be as bad or even worse, because it's not even running, it's not even getting any real power developed. So no load condition power factor is really bad in an induction motor. But as we load it, so on load, we are going to always deliver a real power, mechanical power. So because of which power factor improves, but it can never become unity. It will always become maybe 0.8 or 0.85, not anything more than that. I am rather saying that we should know the phasor diagram, which is very similar to transformer phasor diagram. If I say this is V1, I may have a small core loss component of current. I may have somewhat larger magnetizing current. When I add the two, I should get actually whatever is the sum, which is actually the no load current. Even the power factor I have shown is somewhat better. Generally, it will not be that way. No load power factor is this, right? This is what is the no load power factor angle. So even that angle I am showing around 60, 65 degrees, it can't be like that. It will be more than that. Normally, if it is a well-designed induction motor. If I look at the rotor current I may write it as I2 dash, which is very similar to the current that is reflected from the secondary side of the transformer to the primary. The same way here from the rotor side it's going to get reflected to the stator side. But please note, in the case of transformer, it depended upon what kind of load I connected on the secondary side. Here it is going to depend upon how much load I have put on the shaft. If I put more and more load, it will require more and more torque. If it requires more torque, it will draw more and more current. The slip will be increasing, because of which the current will increase. So here I am going to rather specify what is the rotor current depending upon how much is the load torque on the shaft. So maybe if I have a full load torque, I may have some current like this. Please note, this current is still lagging. It can't be at unity power factor, because I do have X2 dash. I can't ignore X2 dash. So I do have X2 dash. The overall impedance of the rotor circuit becomes R2 by S plus JX2. So very clearly it is inductive in nature. So depending upon how much is the leakage, I am going to have I2 dash lagging behind by some angle, depending upon how much is my leakage reactance. Now I have to add these two, the no load current and this particular rotor current. When I add them together, so let us say this is my no load current. So when I add them together, this is going to be my I1. I1 is the stator current. Which we had been neglecting conveniently. Very often we were doing the parallel circuit parameters, we cancelled out. But this is what is the phasor diagram of an induction motor when I am referring the whole thing to the stator side. Right? So anyway, I migrated from the DC machine to the induction motor. See, again, it depends upon the statement. Generally, what is shown on the nameplate detail is useful output. The nameplate details always give you, especially as a consumer, I would like to know how much my motor can deliver. So that is what is given on the nameplate detail. So I should assume that if the nameplate details are given, that is essentially useful output. That is the way it goes, generally. Power output and power developed are not the same, because power developed in a DC motor will be EB multiplied by IA. Right? What you are giving is VT multiplied by IA as far as the armature is concerned. VT multiplied by IA, you are subtracting IA square RA, which is the armature resistance drop. Right? So that dissipation is gone. You can't do anything. So what is left over is EB multiplied by IA. That is the power developed, minus whatever is the friction and windage losses, if those are given. If those are not given, I would conveniently assume that it is ideal condition, friction and windage losses are 0, if they are not given. Got it? If it is not given, if it is given, please do not assume friction and windage losses to be 0. Then you are essentially reducing your calculation. That's all. The problem statement says a 230 volts, 870 RPM, 100 ampere. 230 volts, 870 RPM, 100 ampere. Separately excited DC motor. Okay. It has RA equal to 0.05 ohm. Okay. It is driving a load, it is coupled to an overhauling load with a torque of 400 Newton meter. So, there is a overhauling torque of 400 Newton meter. Okay. Now it says determine the speed at which the motor can hold the load by regenerative braking. So, at what speed the machine can hold the load by regenerative braking. Okay. So this is what is being asked. First of all, I'll have to tell you what is regenerative braking. So in regenerative braking, normally what we are going to do is, let us say this is my machine, this is a separately excited DC machine, and I am having field here. Okay. If it is actually connected to a voltage supply which is VA like this, right, normally the current is going to flow like this, right. Here is my EB. Fine. So this is normal motoring operation, in which case I am going to have EB equal to VA minus IARA, from which we wrote all the equations and so on and so forth. And field current is a constant, because of which we are going to have TE equal to K phi IA. Maybe K phi is a constant. If I assume, I can simply write K dash multiplied by IA. Right. If I want regenerative braking to be incorporated, what I can do is, either I reduce VA. If it is like a rectifier, I would be able to put a variac or whatever and reduce VA. Or if it is like a battery, I have connected multiple number of batteries, I can remove one of the batteries so that VA will be decreased. If VA is decreased and EB happens to be greater than this decreased VA, originally maybe I had 220 volts here and 210 volts here, which is EB. Maybe I have decreased this now to 200 volts by removing 120 volts battery. And I am not going to definitely have the speed decreased immediately. That's not possible because there is inertia. So I am going to have this to be still 210 volts with plus here and minus here. So what will happen is the current will start flowing in the opposite direction. If the current starts flowing in the opposite direction, if there is a battery, that battery is going to get charged, right? So I am essentially using the kinetic energy stored in my inertia, in my rotational system, that is being converted into electrical energy, and that is being fed back to the battery or the source in whatever way it is. Because of which I am utilizing the process of losing the kinetic energy rather than dissipating it in the external resistance, what I did in dynamic braking. If you may recall, in dynamic braking or rheostatic braking, what we did was to connect a resistance. We had connected a resistance. The field was still there, but what we did was, this EB was circulating a current IA, which was actually getting dissipated. The current was dissipating the power in the form of heat in RB. This is what we did in dynamic braking. So this is dynamic braking or rheostatic braking, because we were connecting a rheostat, whereas this is regenerative braking. Right? So what is going to happen is, IA has reversed its direction, IF has not reversed its direction, so torque gets reversed. TE is reversed. Okay, so I'm going to have a reversal of torque with the speed still remaining in the forward direction, so I would call it as braking. Only difference between rheostatic braking and regenerative braking is regenerative braking I am utilizing the kinetic energy, whereas in rheostatic braking I am dissipating that energy in the form of heat, so I am not utilizing it. Our Delhi Metro and all that are using actually regenerative braking because we don't want to lose out on so much of energy. So generally we use regenerative braking to make sure that all that energy is converted back into electricity and then we utilize it once again. That's what we do. Wake him up. Huh.
If there is also it's like an example of bicycle. It's a regenerative braking system which is adapted for bicycles. So when I apply brake, so
it is actually dissipated in the form of heat in the brake shoes, that is friction. What you are doing as actually braking in any of the petrol based vehicle or diesel based vehicle or your bicycle is you are putting really some amount of friction. You are trying to stop the wheel by putting friction. So it will be dissipated in the form of heat there. That's why if you look at many of the old cars, you will see that the brake pedal and the brake shoes, those get worn and worn out very soon because of the heat generated.
in that scenario, heat is converted into.
You are essentially having again kinetic energy converted into heat, but you are not having much of control, because how much of control my leg can have, foot can have in terms of how much of pressing I am doing. It's kind of difficult. Whereas here I will be able to have a control. If I try to put a resistance here, for example, I can make the current somewhat different. That is not efficiency. If you are talking about quick stopping, maybe that gives a quick stopping, that's what you think. But here also if I put a small resistance, it will give me a very good stopping control. Right? Electrical braking gives you actually very fine control, extremely fine control. That's why the vehicles, generally electric vehicles, will have excellent braking mechanism, if it is designed properly, of course. Right? So this is regenerative braking. If I try to show you in the form of characteristics, this is the speed, this is the torque, and this is going to be my normal characteristics of the DC machine. Right? Maybe the machine was operating at some point here. This was the operating point that we were talking about. Okay? Now, if let us say it is something like a vehicle which is going downhill, right? What will happen? The speed will increase enormously. Whether I like it or not, the speed is going to increase quite a bit. So if the speed increases quite a bit, for what you know, the speed might go beyond rated speed. If the machine is actually going downhill, the vehicle is going downhill, or if it is like an elevator, 4 people have gotten in, it is coming down, there is hardly any control, let's say, it will just go crash. That's what will happen if I don't have any control. But if it is going to go down at a high speed, I'm going to see right away that the torque automatically becomes negative. You see that this is positive torque direction, this is negative torque direction. So when I'm going to have a larger value of speed, even more than no load speed, that is when regenerative braking can take place. If I am talking about a mechanism where the speed can go beyond no load speed because of aiding of gravity. It cannot happen in a mechanism where it is just moving on a plane, right? Because I need to necessarily reduce the battery value, the voltage value, otherwise it cannot happen. So naturally, if regenerative braking has to take place, it has to have a slope, or the gravity has to aid the velocity to become higher than the no load speed. So now with this in mind, let us try to do this problem. Please understand, the moment I say it is overhauling torque, that means this is going to be a negative torque because we are talking about braking. So this is going to be 400 Newton meter, which is actually minus 400 Newton meter. the torque is going to be minus 400 Newton meter. Okay. So this is 230 volts, 870 RPM, 100 ampere. Please remember the data. So I have to say 230 minus whatever is the current, that was 100 ampere I suppose, and how much was the armature resistance? 0.5? 0.05. So this is going to be my EB normally, right? Where did I keep the paper? Okay. So this is what is my EB. How much is it? I have calculated it, but I am not having it right now. 225 volts. Okay. And it is at 870 RPM? Yes. So this is at 870 RPM and at rated excitation, hopefully. Because we are not talking anything about variation in excitation. So which means I can calculate what is K5. So this will be 225 divided by 870 by 60 into 2 pi. So I can calculate what is K5. So what I get as K5 is volts per radians per second, right? So volts second per radian. Tell me the value, whatever it is. Okay. Now what is being said is 400 Newton meter is the overhauling torque, which is actually, I should say, minus 400 Newton meter. So I should say minus 400 divided by this K5 should give me what is the value of IA, which will be actually a negative armature current, which means it is flowing from the armature into the power supply. That's what it means. The current direction is reversed. So this flows from armature to the power supply. Am I right? Now, all I need to do is, what is the value of EB under this condition? Please understand that now the current is flowing this way. And this is EB or EG if it is working as a generator. So I should say EB under regenerative braking will be equal to whatever is the terminal voltage plus IARE, because the current is flowing the other way round. Am I right? The current is exactly flowing in the opposite direction. So whatever is the generated voltage, from that I am going to have IARE drop, rest of it is going to go as the terminal voltage. Right? So I can say in this case VT is still a constant 230, IA I must have gotten here, let me call that as IA dash, RA is 0.05. So I have got clearly what is the value of the voltage. Once I get the voltage, I can just divide it by K5 to get omega. That's it. K5 is already there. So that is the speed at which it will generate a voltage sufficient enough to create a torque of minus 400 Newton meter. That's what it means. I have connected it, let us say, to a fixed voltage battery. It cannot go beyond or above, or, in no way it can go beyond 230. Only because of that regenerative braking is taking place. If I have a variable voltage, if I don't have a variable voltage, only way it can work is having the terminal voltage as a constant, which is what happens in most of the DC motor drives. If you cannot decrease the terminal voltage, what are you going to do? Only way it can happen is if your armature voltage, back EMF, becomes higher than whatever is the terminal voltage. That has become higher probably because it is pulled down by gravity. That's. You will get this EB value to be very clearly greater than 230 because it is VT plus IARE. Right? So IA is governed by the difference between what is EB and what is VT. VT is fixed and EB depends upon the speed. So obviously this can happen only at a speed greater than 870 RPM. It can't happen at 870. Obviously. Is this clear? Yes. Answer is how much? 920? I was getting it to be 920. Yeah, 921 or something. I was getting 920, in fact just 920.4 or something like that. It is coming out to be okay. That's what I think at least. Okay? But this is the method. Forget about the answer. Okay? It says 240 volts unsaturated shunt motor. That means unsaturated essentially means the flux is going to be proportional to IF. That's what it means. Okay? So 240 volts unsaturated shunt motor has an armature resistance including brushes and interpoles of 0.04 ohms. So I would say RA is 0.04 and RF is 100 ohms. Find what resistance must be added to the field circuit to increase the speed from 1200 to 1500 revolutions per minute when the supply current is 200 amperes. So the first subdivision says supply current is 200 amperes. Right? Speed has to be increased from 1200 to 1500 RPM. Okay? So if the supply current is 200 ampere, this consists of both armature current as well as field current. So I should be able to say, first of all, 200 minus IF. IF is 240 divided by 100, which is 2.4 ampere. Right? So this is essentially IA, which is actually IL minus IF. This is what is my IA. Right? And I can calculate definitely under this condition what is the back EMF. 240 minus, I should say 0.04 multiplied by, how much was it? 197.6. So 197.6. This is going to be my EB. Right? So once I get my EB, I can say I would be able to get my K phi or K times IF, whatever. So I can say speed, that is this corresponds to EB divided by 2 pi into 1200 by 60 will give me K phi corresponding to 2.4 ampere of IF. Am I right? Now I want to increase actually my speed to 1500 RPM, for which I have to do field weakening. There is no other way. If I do the field weakening, I should be able to increase the speed. So I want to increase speed to 1500 RPM by field weakening. So let us say the new IF value is equal to IF dash. Line current is not changing. So I should be able to say IA new will be equal to 200 minus IF dash. Right? And I should say 200 minus IF dash is IA new. So 240 minus 0.04 multiplied by 200 minus IF dash will be my EB new. Let me call this as EB dash. Right? But this has to happen at a value of 1500 RPM, right? So if I say this, rather than writing this as K5, I can even write this as maybe this is equal to K5 I have got. So this K5 is actually K into IF dash multiplied by some other constant, or I should say this K5 is equal to K1 multiplied by 2.4. That's what it means. So I should be able to calculate what is K1. K1 is available with me. That's not a problem. So I should be able to write this EB dash should be equal to K1 multiplied by IF dash multiplied by 2 pi into 1500 divided by 60. I'm looking at the new value of back EMF at 1500 RPM, which can be expressed in the form of K1 into the new field current multiplied by 2 pi into 1500 by 60, from which I should be able to solve for IF dash. Is that clear? So IF dash can be solved for. So if I solve for IF dash, so once I solve for IF dash, piece of cake. You should say 240 divided by 100 plus 100 was the original resistance, some R external. I think they are asking for R external, if I am right, equal to IF dash, from which you can get what is R external F. Right? If you look at the next subdivision, with field resistance as in A, so now the field resistance is 100 plus R external F, right? Always this is all proportion, ratio and proportion kind of problems, most of them. So if the field resistance is increased as in A, find the speed when supply current is 100 ampere. You have the field current now, IF dash. So 100 minus IF dash will be your new IA. From that you will calculate what is the drop, right? IA-RA drop. And you have got the new value of EB. So from the new value of EB, you can always calculate what is the speed. But only thing you have to remember is I have to use K times IF dash, not K times IF. Right? So I think rest of the subdivisions will follow suit. It should not be. Part C. Part C is generator. Okay. So part C says, if the machine is run as a generator to give 200 ampere at 240 volts. So in part C, I am going to have 200 ampere at 240 volts as a generator. So 200 plus IF. I don't know whether this is with field current as in B or is it field current as in A. I think I have calculated it with field current as in A in my solutions what I have put, which is 2.4 ampere. So 200 plus IF will be IA as a generator. So I am going to have 202.4 ampere is IA. So from which I can calculate EG equal to 240 plus IA-RA drop. Right? So I would be able to get the generated voltage. We had calculated what is EB at 1200 RPM. This is what was EB at 1200 RPM with IF equal to 2.4 ampere. Now the speed is given as 1200 RPM. So I need to just use the ratio again. That's it. So I can say this is how much? This was how much? 232 something. 0.06 whatever. 0.096. ठीक है, 232.1. Okay. Fine. So 232.1 volts. So I can say 232.1 volts was EB or EG at 1200 RPM and 2.4 ampere of IF. Now EG volts will be, at 1200 RPM and what IF. That's it. Okay? Any further questions? Most of them work on ratio and proportions because we hardly ever give nonlinear portion of the magnetization characteristics very often. We try to confine ourselves as much as possible to linear portion, but if we are going into nonlinear portion, we may say, although the increase in the current is by so much, armature reaction weakens the flux by so much percentage. That's what we say. This is not IF, this is IF2 dash. This is also IF2 dash. So I should say 200 plus IF2 dash multiplied by RA plus 240 will be equal to EG, which is proportional to K1 multiplied by IF2 dash multiplied by 1200 RPM, which will be 125.6 radians per second.